100 meters underground, straddling the border of France and Switzerland, a machine is tearing reality apart one proton at a time. The Large Hadron Collider fires particles around a 16.5-mile ring at 99.9% the speed of light. The collisions reach nearly 10 trillion degrees. And the data coming back is breaking the rulebook physicists have trusted for 50 years. We're going inside the machine. We'll cover the particles that behave wrong, the hidden universe too small to see, and a theory about the vacuum of space that is almost too terrifying to say out loud. If this kind of content hits different for you, subscribe. Let's go. There is a tunnel beneath your feet right now. You just can't feel it. Well, not beneath your feet specifically, but somewhere under the green farmland, along the border of France and Switzerland, buried 100 meters underground, sits the most powerful machine the human race has ever built. It doesn't look like much from the surface. A few industrial buildings, some ventilation shafts poking out of the ground, power lines running toward the horizon. Nothing about the outside tells you what's happening below. What's happening below is this. Scientists are smashing protons together so hard that the collisions recreate conditions that last existed a fraction of a second after the universe was born. Let that image sit for a second. A fraction of a second after everything began. The machine is called the Large Hadron Collider. It runs in a circular tunnel measuring 16.5 miles around. If you drove that loop on a highway, it would take you about 20 minutes. Underground, inside tubes thinner than your arm, proton beams race around that same loop 11,000 times every single second. Not 11 times, 11,000. The magnets that keep those beams locked in their path are cooled to minus 456 degrees Fahrenheit. That is colder than the surface of Pluto, colder than most of deep space. Engineers had to build the coldest large-scale object on Earth just to keep the machine running straight. The collider took decades to design and build. Thousands of scientists from over 100 countries worked on it. When it first powered on in 2008, there were people outside the facility holding signs that said it would destroy the world. The theory was that collisions this powerful could create a tiny black hole that would swallow the Earth from the inside. Scientists checked the math carefully. They were confident that wouldn't happen. They turned it on anyway. The world did not end, but something else happened instead, something quieter, and in the long run, maybe more unsettling. The machine started finding things that didn't fit, not dramatic explosions or impossible readings, just small numbers that were slightly off, particle behaviors that deviated by fractions, so tiny they seemed like rounding errors. Except they kept showing up, again and again, in different experiments, run by different teams, using different detectors. The rule book that physicists had trusted for 50 years started showing cracks, and the deeper scientists looked, the more cracks they found. There are roughly 2,700 scientists working on the collider right now. Many of them are chasing the same thing, evidence of a layer of reality that exists below what any machine has ever been able to see. A layer where the current rules might break down completely, where forces and particles nobody has named yet could be operating in ways that would rewrite every physics textbook on Earth. That search is what this story is about. The machine buried under Europe is the most precise instrument ever built. It runs on enough electricity to power a small city. Its detectors weigh more than the Eiffel Tower, and after decades of searching, it is getting close to something. What that something is, nobody fully agrees on yet, but the data keeps pointing in the same direction, and the scientists who spend their lives staring at that data are starting to look genuinely nervous. For 50 years, one document has ruled physics. Scientists call it the Standard Model. It's a mathematical framework, a precise set of equations that describes every particle ever detected and explains how 3 of the 4 fundamental forces in the universe operate. It covers the electromagnetic force that makes electricity work, the force that holds atomic nuclei together, and the force responsible for radioactive decay. It is the most successfully tested theory in the history of science. Experiments have confirmed its predictions to an accuracy of 1 part in a billion. So when physicists say it's breaking, that matters. The Standard Model came together through decades of work across the 20th century. Every particle it predicted was eventually found in labs. The last missing piece was called the Higgs boson, a particle tied to the mechanism that gives matter its mass. Scientists at the Collider found it in 2012, and the physics community celebrated. The rulebook was complete. Then the questions started. The Standard Model works perfectly inside its own borders, inside a lab, under controlled conditions, at the scales humans have been able to test. But zoom out to the actual universe, and the cracks appear fast. The model has absolutely nothing to say about dark matter, the invisible substance that makes up 85% of all mass in the cosmos. It cannot explain dark energy, the force causing the universe to expand faster and faster every year. And it gives no answer to one of the biggest puzzles in all of science: why anything exists at all. According to the Standard Model, the Big Bang should have created equal amounts of matter and antimatter. Equal amounts. And when matter and antimatter meet, they annihilate each other completely. So if the equations were right, the universe should have destroyed itself in the first instant of its existence. Everything cancelling everything out. Nothing left. Clearly, something survived. You're listening to proof of that. Something in the early universe tipped the scales. A tiny imbalance. Matter won by a fraction. And that fraction became every star, every planet, every atom in your body. But the Standard Model cannot tell us what caused that imbalance. The answer is somewhere outside the rulebook. Here is what makes this uncomfortable. This isn't an old problem. Physicists have known about these gaps for decades. They've built extensions, added theories, made adjustments, and nothing has filled the holes cleanly. And recently, something new started showing up in the data. Particle behaviors inside the collider that deviate from what the Standard Model predicts. Tiny deviations, barely measurable, but they show up repeatedly across multiple experiments under conditions designed to eliminate errors. The numbers keep coming back slightly wrong in the same direction. To a physicist, that pattern means something. Random errors scatter in all directions. Systematic signals point the same way every time. The data is pointing. Scientists are now seriously discussing the possibility that the Standard Model is not just incomplete. They're asking whether it's fundamentally wrong at scales smaller than anything ever measured. Whether the universe is operating on a deeper set of rules, hidden beneath the current limit of human detection. Finding those rules would rank as the biggest scientific discovery in human history. Bigger than gravity, bigger than relativity, bigger than the discovery of DNA. And the hunt for them requires going somewhere no instrument has ever reached before. Get ready, because where we're going next makes the atom look enormous. July 4th, 2012 started like any other summer morning at the facility. Then, at a packed auditorium in Geneva, a physicist stood at the podium and announced that after nearly 50 years of searching, they had found it, the Higgs boson, the so-called God particle. One of the scientists in the room started crying. Another stood up and clapped so hard his hands turned red. Peter Higgs, the man who theorized the particle's existence back in 1964, was sitting in the front row. He was 83 years old. He had waited his entire adult life for this moment. The discovery was real. The particle was real. Its mass matched the predictions almost exactly. It was, by any measure, one of the greatest moments in the history of science. And almost immediately, the celebration turned into a problem. The Higgs boson had a confirmed mass of about 125 giga-electron-volts. That sounds like a technical detail, and it would be, except for what that specific number implies when you feed it into the equations governing the stability of the entire universe. The number sits in a dangerous zone, too light, and the vacuum of space would be completely stable forever. too heavy, and the vacuum would be clearly unstable, already collapsing. But right at 125 gigaelectronvolts, the math lands in what physicists call a metastable region, a middle ground, a state that appears stable, could last for billions of years, but given the right trigger could snap into something else entirely. Think of it like a ball sitting in a shallow dip on a hillside. It looks still, it feels stable, but give it enough of a push, and it rolls off the edge. The universe might be that ball. Scientists stress that this isn't a prediction of doom for any time soon. The timescales involved are so vast, they stretch beyond anything a human brain can picture. But the unsettling part is the principle. The Higgs boson, the particle physicists spent decades hunting, turned out to carry a mass that hints at something fragile underneath reality itself. And the discovery didn't close the chapter. It opened a new one, because the Higgs field, the invisible energy field the boson is connected to, is the thing that gives all particles their mass. Every electron, every quark, in every atom of your body has mass because it interacts with this field. The Higgs boson is proof the field is real, but the field itself raises a new set of questions physicists still can't answer. Why does the Higgs field have the strength it has? The standard model gives no explanation. The number just sits there, confirmed but unexplained. To many scientists, an unexplained number in the equations is not an answer. It is a sign that something deeper is missing, something controlling the Higgs field from a scale smaller than anything detected, something hiding below the current limit of observation. That possibility is what pushed researchers toward an entirely new frontier, a scale of existence so small that the entire atom looks like a galaxy by comparison. And the physics hiding there might change everything we think we know. Imagine you're looking at a photograph of a city from 30,000 feet in the air. You can see the grid of streets, the parks, the shape of the coastline. From up there, it looks complete, like you're seeing everything. But zoom in close enough and you realize you can't see the people. Zoom in further and you can't see the cars. Get down to street level and there's an entire world of detail that was invisible from the plane. Conversations happening, doors opening, insects crawling across the pavement. Now imagine that street level is the atom, and below the atom there are more levels, smaller and smaller, each one hiding something the level above couldn't see. Physicists believe there is a layer of reality so deep, so unimaginably small, that the forces operating down there would explain everything the standard model can't. They call it the zeptuniverse. A zeptometer is 1/60th of a meter. If you lined up 1 billion atoms side by side, their combined width would still be incomparably large compared to 1 zeptometer. The current collider can probe down to about 50 zeptometers, which is already far smaller than anything visible to human senses. The zeptuniverse sits at 10 to the power of -21 meters. That's roughly 20 times smaller than what the collider can currently reach. Scientists can't see it directly. No instrument built today can reach it. So why do physicists believe it exists? Because the math keeps pointing there. When researchers calculate where the gaps in the standard model are located, when they trace the origin of the anomalies showing up in the collision data, when they work backward from what the Higgs boson's mass implies, the calculations keep landing at the same address, the zeptoscale, a region of reality just below the current limit of detection, where new forces and undiscovered particles may be operating in ways that shape everything above them. This is the frontier physicists are most excited and most frustrated by simultaneously. Excited because the evidence suggests something real is there. Frustrated because reaching it directly might require a collider dozens of times more powerful than anything built today. Something the size of a city. Something that would take generations to fund and build. So, instead of seeing the zeptuniverse directly, researchers hunt for its shadow. Every particle interaction that happens at detectable scales sends ripples backward from whatever lies below. Like how you can know a stone landed in a lake you can't see just by watching the ripples reach the shore. If new particles or forces exist at the zeptoscale, Their presence will distort the behavior of known particles in measurable ways. Finding those distortions is the entire strategy, and some researchers believe the distortions are already showing up in the data. 7 specific particle interactions, each one so rare it challenges the limits of what the collider can track, are now sitting at the center of that hunt. And the numbers coming back from those interactions are not matching the standard model's predictions, which means something down there might be pushing back. There's a classic trick in physics. If you can't observe something directly, observe what it does to everything around it. Nobody has ever seen a black hole with a direct photograph of the object itself. What we see are the jets of material being sucked in, the distortion of light bending around the gravitational pull, the behavior of nearby stars being flung into strange orbits. The black hole announces itself through its effects on everything else. The Zeptuniverse works the same way. Scientists at the collider can't fire a beam at something 20 times smaller than their detectors can reach. The physics won't allow it with current technology. So instead, they designed a different kind of experiment. Rather than looking at the hidden scale directly, they study specific particle interactions at detectable scales with extreme precision. Precision so extreme that any tiny influence from below would show up as a measurable deviation in the numbers. The logic works like this. If you know exactly how a particle should behave based on every known force and every known particle in the standard model, and you then measure its actual behavior thousands of times under controlled conditions, any consistent difference between prediction and reality becomes a signal, a whisper from below. The challenge is making the measurement precise enough to hear that whisper. The collider generates millions of particle collisions every second. Most of them produce common, well-understood outcomes that physicists have mapped in exhaustive detail. But scattered across all those ordinary collisions are a handful of ultra-rare events. Interactions that the standard model says should almost never happen. Events so unlikely that out of billions of collisions, only a few clean examples survive. Those rare events are the most sensitive instruments scientists have, because the rarer the process, the more a hidden influence from below can change its rate. A common event happening a billion times might shift by a few percent if something unknown nudges it. A rare event happening once in 10 billion collisions might double or triple its rate if the same unknown force pushes it. The signal is louder on the rare events, even though they're harder to catch. This is what makes the next set of experiments so important. Teams at the collider and at a separate facility in Japan are measuring the decay rates of specific particles with strange and bottom quarks with a level of precision that wasn't achievable 10 years ago. Quarks are the building blocks inside protons and neutrons, the particles that make up every atomic nucleus. They come in different types, and some of those types produce extremely rare decay patterns when they break down. If those decay rates match the standard model's predictions exactly, it means the model is holding, at least at that scale. But if the rates come back even slightly different, consistently, across multiple independent measurements, it means something unknown is influencing the outcome. Something from a layer of reality the detectors can't directly see. The measurements are already showing hints, small deviations, consistent directions. Scientists are careful to say they have not confirmed new physics yet. The data needs more collisions, more statistics, more independent verification. But the hints are there, and the team chasing the most dramatic example of this found it inside one of the smallest and strangest particles in the known universe. A particle called the kaon, and what it did in a recent experiment stopped the physics community cold. Picture a crime scene with no body. The detectives know something happened. The evidence is everywhere. Footprints in the wrong place, a door opened from the inside, dust disturbed in a pattern that doesn't match anyone who was supposed to be there. No suspect in custody, no witness, just the aftermath of something that shouldn't have occurred. That's essentially what physicists are looking at right now. They've identified 7 specific particle interactions, 7 types of particle decay, where the evidence keeps suggesting something interfered. something that has no name in the current rulebook. The physics community calls them the Magnificent Seven. Each one involves particles containing quarks, the smallest known building blocks of matter, breaking apart and transforming into lighter particles in ways that the standard model can predict with extraordinary precision. The key word there is can, because the predictions keep failing to match the measurements. To understand why this matters, you need a picture of what a particle decay actually is. Imagine a heavy object sitting on a table. Given enough time, the laws of physics will cause it to break apart into lighter, more stable pieces. That breakdown follows rules. Specific pieces, in specific proportions, released at specific rates. If you measured 1,000,000 of those breakdowns and found that twice as many heavy pieces survived as the rules predicted, you'd know something was pushing back against the expected process. That is exactly what the Magnificent Seven experiments are testing. Scientists track how often specific rare decays happen and compare the measured rate to the standard model's prediction. For most common processes, the two match almost perfectly. But for these 7 ultra-rare interactions, the match is not clean. The rates are off, consistently, across independent experiment, in directions that suggest something is influencing the process from outside the current model. 2 of these interactions involve particles called B mesons, which contain bottom quarks. Another involves particles called D mesons. And 2 of the most sensitive involve a particle called the kaon, which contains a strange quark. The kaon experiments are currently producing the most dramatic hints of all. What makes these 7 specific decays so powerful as detection tools is their rarity. These are quantum events so unlikely that gathering enough examples to produce reliable statistics requires years of running the machine at full power. The standard model predicts these decays with enormous precision, so any deviation, even a small one, carries massive weight. Each of the Magnificent Seven is being studied simultaneously by different teams using different detectors and different methods. Scientists do this deliberately. Independent confirmation is the only way to rule out instrument errors, calculation mistakes, or statistical flukes. And here is what has the physics community quietly buzzing right now. Several of the 7 are showing deviations in the same direction. Different teams, different experiments, different particles, same direction. When multiple independent measurements all tilt the same way, scientists start paying very close attention. The most precisely measured of all 7 comes from an experiment that almost didn't happen. A team targeting a kaon decay so rare that the physicists who first proposed measuring it were told it might be impossible. The event they were hunting should only occur once in every 10 billion kaon decays. And the rate they measured wasn't what the rulebook predicted. You have never touched a quark. You have never seen one, felt one, or isolated one in a lab. Despite being the fundamental building blocks of protons and neutrons, quarks have never existed alone outside of a particle collision for longer than a fraction of an instant. They are permanently locked inside larger particles, bound together by forces so powerful that the harder you try to pull 2 quarks apart, the more energy you pump into the space between them, and that energy spontaneously creates new quarks to fill the gap. Trying to isolate a quark is like trying to cut a rubber band in half. You just end up with 2 rubber bands. There are 6 types, called flavors, of quarks: up, down, strange, charm, bottom, and top. The names are arbitrary. They don't describe anything physical about the particles. They're just labels physicists assign to distinguish 6 genuinely different objects with different masses and different behaviors. The strange quark is the 3rd lightest. It was discovered in the 1950s when physicists noticed that certain particles created in cosmic ray collisions lived much longer than they should have before decaying. Something was making them hesitate. Something was slowing their breakdown. That strange behavior gave the particle its name, and eventually, scientists traced the effect back to the quark inside. Strange quarks are the key ingredient in kaons, the particles sitting at the center of the most sensitive decay experiments running today. A kaon is essentially a strange quark paired with an up or down antiquark. When a kaon decays, the strange quark transforms through a sequence of interactions governed by the weak nuclear force, the force responsible for radioactive decay. The Standard Model describes this transformation in precise mathematical detail. The problem is, the math and the measurements are starting to pull apart. Inside the collider, strange quarks don't decay in a vacuum. They interact with every known force and every known virtual particle that quantum mechanics allows to appear temporarily in the space around them. All of those interactions nudge the decay rate slightly. Physicists account for every single one. They have to, because the goal is to measure the final decay rate with enough precision that any leftover deviation, any rate that can't be explained by the known forces, becomes evidence of something unknown. Strange quarks, specifically inside kaons, are ideal for this because their decay sequences involve processes that are extraordinarily rare. The rarity amplifies any hidden influence. A force too weak to noticeably affect a common process might change a rare one dramatically, and the rate coming back from the experiments isn't lining up. The strange quark might be reacting to something physicists haven't named yet, a force from the zeptoscale, a particle too heavy to appear directly in the detector but light enough to influence the decay from below the threshold of detection, or something else entirely, something that doesn't fit neatly into any existing theory. Scientists stress they haven't confirmed new physics yet. The deviations are real, but the statistical certainty needed to make an official announcement hasn't been reached. More data is required, more collisions, more events, which is exactly why the experiment running inside a separate building, away from the main collider, recently produced a measurement that made physicists stop and stare at their screens. The NA62 experiment does not look like the future of physics. It sits in a long, narrow hall inside a separate facility at the collider complex. There are no giant circular tunnels, no detectors the size of apartment buildings, just a focused beam of kaons, a series of carefully arranged sensors, and a team of physicists hunting for an event so rare that finding even a handful of clean examples counts as a major result. They were hunting for a specific decay, a positively charged kaon breaking apart into a positively charged pion plus a neutrino plus an antineutrino. The Standard Model predicts this exact sequence should happen once in every 10 billion kaon decays, 1 in 10 billion. For comparison, the odds of winning a major national lottery are roughly 1 in 300 million. This decay is 30 times rarer than that, and scientists needed to detect it reliably enough to count how often it happens. In 2024, the team published their result. They had captured enough events to produce a meaningful rate measurement, and the rate they measured was higher than the Standard Model's prediction, not by a random scatter in all directions, consistently higher in a way that points toward the same kind of deviation showing up in the other experiments chasing the Magnificent Seven. Here's why that matters. The Standard Model predicts this specific decay with some of the greatest precision in all of physics. The calculation is clean because it involves a short-distance quantum interaction, meaning fewer of the messy, hard-to-calculate effects that cloud other measurements. Physicists trust this prediction more than almost any other in the entire model, so a deviation here carries more weight than a deviation somewhere harder to calculate. Think of it like a measuring tape that you've calibrated perfectly against a known standard. If that tape, after all that calibration, gives you a reading that doesn't match the object you're measuring, you take it seriously. The tape is right. Something about the object is different from what you expected. The kaon is giving a different reading. Something is influencing its decay rate. Either a particle too heavy to show up directly in the detector is acting as a messenger behind the scenes, a so-called ghost particle pulling strings without being seen, or an undiscovered force is nudging the process in a direction the Standard Model doesn't account for. Neither possibility fits neatly into existing physics, both possibilities would require new physics beyond the standard model. The team was careful in how they announced the result. The deviation is real. The measurement is solid. But the statistical certainty needed for a formal discovery claim in particle physics is extremely high, and the result sits just below that threshold. More data would push it over, or pull it back. The machine needs more runtime, more kaons, more decays, and on the other side of the world, a completely separate team of scientists heard about the result and started running their own version of the experiment. Their goal: confirm or contradict the finding using a different method, different equipment, and a different type of kaon. If both experiments point the same way, the standard model's days as an unchallenged rulebook are numbered. Roughly 6,000 miles from the facility in Switzerland, in a concrete building tucked inside a research campus in Tokai, Japan, a different team of physicists is running a different version of the same hunt. The experiment is called COTO. It targets a neutral kaon, the uncharged version of the same particle the Swiss team studied. Neutral kaons decay differently from charged ones. The specific process COTO is measuring is even rarer. The standard model predicts it should happen roughly 3 times in every 100 billion neutral kaon decays. Finding even a single confirmed example of this event in a reasonable runtime is an achievement. Finding enough to build a reliable rate measurement is a years-long project. Why build 2 separate experiments chasing the same type of event on opposite sides of the planet? Because independent confirmation is the most powerful tool in science. History is full of signals that turned out to be noise, instrument errors that looked like discoveries, statistical flukes that vanished when more data arrived. The scientific community learned this the hard way over decades, and the response was a culture of intense skepticism toward any single result, no matter how clean it looks. If 2 completely independent experiments, using different equipment, different kaon types, different analysis methods, and different physics teams arrive at consistent deviations from the same standard model prediction, the probability that both are wrong in the same direction by coincidence becomes vanishingly small. COTO has been running since 2013, and the results have been a source of tension and excitement in the physics community. In 2019, the team announced a preliminary result showing more events than the standard model predicted. The physics world lit up. Physicists started publishing papers exploring what kind of new particle could explain the excess. Then further analysis revealed that some of the excess could potentially be explained by background events the team hadn't fully accounted for. The excitement cooled, but the mystery didn't disappear. The hunt continued. Detector upgrades were made, analysis methods were refined, and as the NA62 team in Switzerland published their own higher-than-predicted rate in 2024, COTO's newer dataset is now being analyzed with those results in mind. The 2 experiments are converging on the same territory from different angles. If both land consistently above the standard model's prediction, the case for new physics becomes extremely difficult to ignore. Physicists have a threshold for claiming a discovery, and it's very high by design, but the direction of travel in both experiments is pointing the same way. What could cause this? Several possibilities are being seriously studied. A new heavy particle, sometimes called a leptoquark, that mediates interactions between quarks and leptons in ways the standard model doesn't include. Extensions of the Higgs sector, meaning additional Higgs-like particles that influence rare decays, or entirely new symmetries of nature, operating at the zeptoscale. Each possibility, if confirmed, would trigger a complete restructuring of particle physics. And the restructuring might go far deeper than just adding new particles to the list. Some of the proposed explanations touch on the most foundational and most disturbing mystery in all of physics. Why does matter exist at all? And why didn't it destroy itself at the very beginning? Galaxies should fly apart. That's the conclusion you reach when you add up all the visible matter in a galaxy, calculate the gravitational pull it generates, and then measure how fast the outer stars are actually orbiting the center. The math doesn't work. The outer stars are moving too fast, way too fast. At those speeds, the gravitational pull from all the visible stars, gas, and dust combined should be completely insufficient to hold the galaxy together. The outer stars should spin off into deep space. They don't. Every galaxy we've ever observed holds together. Something is providing the extra gravitational pull, something massive, something that doesn't emit light, doesn't reflect light, doesn't absorb light in any way we can detect. Something completely invisible to every telescope ever built. Scientists call it dark matter. And here is the number that should stop you in your tracks. Dark matter makes up approximately 85% of all mass in the universe. The stuff you can see, every star, every planet, every cloud of gas, every atom that has ever been measured, is only 15% of the total mass. The dominant component of the universe is something humanity has never directly detected. That is the reality of the cosmos we live in, mostly invisible, mostly unknown. The evidence for dark matter is overwhelming and comes from multiple independent directions. The galaxy rotation problem is one, but there's also gravitational lensing, where light from distant galaxies bends around regions of space that appear to contain no visible matter at all, curving around something massive and unseen. There's the structure of the cosmic web, the large-scale arrangement of galaxies across the universe, which only makes mathematical sense if dark matter is present in enormous quantities during the early universe to act as a gravitational scaffold. Everywhere scientists look, the fingerprints of dark matter show up, but the particle itself has never appeared in any detector. That absence is becoming a major problem. Physicists had good theoretical reasons to expect dark matter to show up in collider experiments. Many of the most popular theories predicted that dark matter particles should be created in high-energy collisions and then detected by the missing energy they carry away without interacting with the detector. The first run of the collider searched for exactly this signature, found nothing. A second run, at higher energy, searched again, found nothing. Current experiments are still searching. The silence is not proof dark matter isn't there. Detection is extraordinarily difficult for particles that barely interact with anything. But the silence is forcing physicists to consider alternatives they were initially reluctant to take seriously. One alternative is deeply unsettling. Several physicists have proposed that dark matter isn't a particle at all. They suggest the gravitational anomalies could mean our theory of gravity itself is incomplete. That gravity at very large scales behaves differently from how Einstein described it. If that's true, then the framework physicists use to describe space, time, and cosmic structure needs fundamental revision. The collider can't directly test this idea, but it can search for related particles and forces that might connect to the dark matter problem. And if any of the Magnificent Seven experiments confirm new physics, the leading candidate explanations all have connections to the dark matter sector, which means the invisible majority of the universe and the strange kaon decays might be symptoms of the same hidden physics. And that connection gets stranger the deeper you go. Isaac Newton described gravity as a force. Albert Einstein redescribed it as a curvature in the fabric of space and time. Both descriptions have been tested to extraordinary precision at the scales humans can probe, and both work. Within the solar system, Einstein's equations predict the behavior of every planet, every moon, every passing comet, with accuracy that borders on perfect. The global positioning system relies on corrections for relativistic time distortion, and it works. Gravitational waves, predicted by Einstein a century ago, have now been directly detected from colliding black holes billions of light years away. General relativity is one of the best confirmed theories in science. But at the scale of entire galaxies and galaxy clusters, something goes wrong. The equations that work flawlessly inside the solar system produce the wrong answer when applied to the rotation of galaxies. The standard fix is dark matter, an invisible mass that provides the extra gravity needed to match the observations. Most physicists accept this fix. It works numerically. It fits a huge range of observations across different scales. And there are good theoretical reasons within particle physics to think heavy, invisible particles could exist. But a small group of physicists have spent decades arguing for a different possibility. What if gravity itself is slightly different at very low accelerations? What if Einstein's equations, while accurate in strong gravitational fields, need a small modification in the weak field limit that describes the outer edges of galaxies? This idea has a name: modified Newtonian dynamics. Physicists proposed a modification to the gravitational law at very low accelerations, and the modified equations reproduce galaxy rotation curves without any dark matter at all. For spiral galaxies, the fit is striking. The modification predicts a precise relationship between the luminosity of a galaxy and its rotation speed, and observations match that prediction across dozens of galaxies, spanning a wide range of sizes. But modified gravity has serious problems at larger scales. Clusters of galaxies and the large-scale cosmic structure of the universe are much harder to explain without dark matter as a scaffold. The cosmic microwave background, the faint afterglow of the Big Bang, carries patterns that match dark matter models far better than modified gravity models. So neither camp has won. Two competing explanations for the same observation, and decades of data that fit one interpretation in some contexts and the other in others. This is deeply unusual in physics. The universe is supposed to have one set of rules, one description of gravity, consistent across all scales. The possibility that both explanations are partially right, that dark matter exists and gravity is slightly modified at large scales, is being seriously explored but hasn't resolved anything cleanly. The collider can't directly test modified gravity, but it can search for dark matter particles in ways that would eliminate the particle explanation if they don't show up even in upgraded experiments. If the next generation of experiments run at 10 times the collision rate find nothing, the pressure on the gravity modification side of the argument increases significantly. Physics rarely likes a situation where the fundamental rules of the universe are contested. Right now, they are, and that tension connects to a mystery so deep it touches the question of why you exist. Why matter won the very first battle it ever fought. At the moment of the Big Bang, physics says matter and antimatter were created in equal amounts. Every particle created had an antiparticle twin created alongside it, electrons and positrons, protons and antiprotons. For every piece of matter, a mirror image of equal mass and opposite charge. And when matter meets its antimatter twin, both are annihilated. They vanish in a burst of energy, completely, totally, leaving nothing behind. If the standard model is correct, the universe should have annihilated itself in the first fraction of a second after it began. Complete mutual destruction, nothing surviving. A cosmos of pure energy and emptiness. Instead, you exist. The atoms in your body are made of matter. The chair you're sitting on is made of matter. Every star in every galaxy in the observable universe is made of matter. Antimatter exists in tiny, fleeting amounts, created briefly in particle collisions and in certain radioactive decays, but immediately annihilated upon contact with any nearby matter. The universe is overwhelmingly made of one type, and physics cannot explain why. This asymmetry has a technical name: baryogenesis, the process by which matter came to dominate over antimatter in the early universe. And despite decades of work, no one has found a satisfying explanation. The standard model does include a small imbalance between how matter and antimatter behave. This imbalance is called charge parity violation. Scientists discovered the first hints of it in the 1960s by studying the decay of kaons. Different types of kaons decay at slightly different rates depending on whether they contain matter or antimatter components. This tiny asymmetry was the first experimental evidence that matter and antimatter are not perfectly symmetric. But the asymmetry measured in the standard model is far too small, by a factor of billions. The tiny imbalance that physics currently accounts for could not have produced a universe dominated by matter. Something much larger tipped the scales, something outside the model. Physicists have been searching for additional sources of charge parity violation in other particle systems. B mesons, which contain bottom quarks, have been studied intensively at collider experiments around the world. Additional asymmetries have been found. They're real, and they're still too small to explain the universe you live in. The Magnificent Seven experiments are partly a search for this missing asymmetry. If new particles or new forces are influencing the decay rates of kaons and B mesons in ways the standard model doesn't account for, those same new forces might carry a larger charge parity violation, large enough to explain why matter survived. The stakes here go beyond academic curiosity. The existence of stars, planets, chemistry, biology, and human consciousness is the direct consequence of matter winning over antimatter by a fraction in the first instant of time. Finding the mechanism that caused that victory would be one of the most profound answers in the history of science, and the experiments that might reveal it are already running, which means understanding how the detectors actually work becomes important, because the technology capturing these hints of new physics is itself one of the most extraordinary machines ever built. At the moment, two proton beams collide inside the Large Hadron Collider. Something extraordinary happens. Hundreds of new particles spray outward in every direction from the collision point. They arrive at the surrounding detectors in less than a billionth of a second. Each particle leaves a distinct signature as it passes through different layers of the detector. Some are charged and curve in the magnetic field. Some deposit energy in specific ways. Some pass through certain materials and stop. Some barely interact with anything at all. A single collision lasts a fraction of a second, and the collider produces roughly 40 million collisions every second. The detectors have to capture all of it. The two largest detectors at the facility are called Atlas and CMS. They sit at opposite ends of the ring, each one surrounding a collision point and recording the aftermath. Both are built like enormous multi-layered onions, with each layer serving a specific detection function. The innermost layers track the precise paths of charged particles. The middle layers measure energy deposits. The outermost layers capture the particles that make it farthest from the collision point. The CMS detector, one of the two main instruments, weighs 14,000 tons. That makes it heavier than the entire Eiffel Tower. It fills a chamber the size of a 5-story building. Its central component is a massive superconducting magnet that generates a field strong enough to bend the paths of fast-moving charged particles. Without that bending, you can't measure particle momentum, and without momentum, the physics falls apart. Inside, CMS are crystals made from a material called lead tungstate. They are completely transparent, like clear glass, but they are denser than iron. When a particle hits one of these crystals, the crystal flashes with light. Sensitive electronic sensors around the crystal capture that flash and convert it into a digital signal. The pattern and intensity of the flashes tell physicists what type of particle hit the crystal and how much energy it carried. The detectors photograph every collision at 40 million frames per second. The raw data from that imaging rate would be completely unmanageable. The facility generates over 90 petabytes of data every year, equivalent to around 20 million 4-drawer filing cabinets packed full of documents. Storing and analyzing all of it is physically impossible. So a sophisticated filtering system triggers on specific patterns in real time, selecting only the most interesting collisions to record fully, and discarding the vast majority in an instant. This filtering means there is a real possibility that some genuinely interesting events get thrown away before anyone can look at them. The filter has to make decisions in microseconds. Physicists design the filter rules carefully to preserve the rarest and most theoretically significant event types. The rare kaon decays and B meson anomalies are exactly the type of events those filters are tuned to keep. Every particle track saved, every energy deposit recorded, adds to the statistical pool that determines whether the deviations from the standard model are real signals or background noise. The detectors are extraordinarily sensitive. But even at this level of precision, one aspect of the physical environment causes a headache nobody expected: the moon. The tunnel is deep underground. It is sealed from the surface. The entire machine operates in a vacuum colder than outer space. And yet, twice a day, the orbit of the moon changes the path of the proton beams. Not dramatically. The shift is measured in fractions of a millimeter, but fractions of a millimeter matter enormously when you're trying to steer a beam of protons traveling at 99.9% the speed of light through a tube less than 4 inches across. A tiny shift in the beam path changes where the collisions happen, which changes the geometry the detectors are calibrated to expect, which can introduce errors into the measurements. The effect is gravitational. As the moon moves through its orbit, its gravitational pull causes the Earth's crust to flex very slightly in what geologists call earth tides. The ground the collider tunnel sits in rises and falls by a few inches twice a day as the crust responds to the moon's pull. The 16.5-mile circular tunnel deforms along with the ground around it. The precise circular geometry the engineers built changes shape slightly with the tidal cycle. Engineers at the facility discovered this effect during the first operations of an earlier machine in the same tunnel. They noticed that the beam required constant small adjustments at a rhythm matching the lunar orbital cycle. Once they understood the cause, they built correction systems to compensate. Today, the control systems monitor the beam position continuously and apply thousands of tiny magnetic corrections every second to keep the beam on track. Part of those corrections account for the slow tidal shift in the tunnel geometry caused by the moon overhead. The same moon that causes ocean tides on the surface is being actively corrected for in real time in a particle accelerator 100 meters underground. This is one of those details that lands differently once you sit with it. The most precise physics experiment in the history of science has to account for the gravitational influence of an object 239,000 miles away. The universe refuses to let the experiment operate in isolation. Everything connects to everything else. There are other environmental effects the engineers track and correct for. The water level in Lake Geneva, several miles away, changes seasonally, and its mass redistributes slightly, altering the gravitational field around the tunnel by a tiny but measurable amount. The passage of underground trains in the Geneva suburbs was tracked during the early years of the facility because the trains caused vibrations in the rock that could theoretically affect the beam. Particle physics, at this level of precision, requires the entire physical environment around the experiment to be understood and accounted for. The same precision that makes the environmental corrections necessary is the same precision that makes the measurements of kaon decays meaningful. If the machine and its environment are understood so well that the trajectory of the moon overhead is being corrected for in real time, then a deviation of a few percent in a rare particle decay rate carries real weight. The machine is accurate enough to detect a whisper from a hidden universe. It just needs enough energy to push deeper, which is exactly what makes what's happening inside the beam pipes so remarkable. A vacuum more empty than anything on the surface of the Earth, and conditions inside the collisions that recreate the first instant of the universe. The Large Hadron Collider exists in two extreme states simultaneously. The beam pipes, the tubes the protons travel through, contain one of the most perfect vacuums ever created on Earth. The pressure inside is roughly 10 times lower than the pressure on the surface of the moon. The moon has essentially no atmosphere. Its surface sits exposed to the raw vacuum of space, and the beam pipes are emptier than that. This vacuum is not just for show. A single proton traveling at nearly the speed of light has enough energy that even a collision with a stray gas molecule inside the pipe would scatter it off course. To keep billions of protons traveling in a tight, controlled beam for hours, the tube they travel through has to be as close to perfectly empty as engineering allows. Creating that vacuum requires pumping chambers along the entire length of the 16.5-mile tunnel. The system pulls out virtually every air molecule from the pipes, working continuously against the slow outgassing of the metal tube walls. Achieving and maintaining this vacuum is a continuous engineering effort that runs for the entire duration of a physics run. While the beam pipes are almost perfectly empty and extraordinarily cold, the magnets that steer the beams sit at the other extreme of temperature, minus 456 degrees Fahrenheit. This temperature, achievable only with liquid helium cooling systems, is required to keep the magnets in a superconducting state. At that temperature, the electrical resistance of the magnet coils drops to essentially zero. Current flows through the coils with no energy loss. This allows the magnets to generate a field strong enough to bend the path of protons moving at near light speed. At room temperature, generating that field would require so much electricity that it would be physically and economically impossible. So the machine sits in this strange dual state: beam pipes emptier than the moon's surface, magnets colder than the outer planets, protons racing through this engineered cold emptiness at speeds that compress relativistic time. And then, the collision. When two protons meet inside the detector, the energy concentrated at the collision point reaches nearly 10 trillion degrees Fahrenheit. 10 trillion. The core of the Sun reaches about 27 million degrees. The collider's collision temperature is roughly 400,000 times hotter than that. At this temperature, matter as we normally experience it ceases to exist. Protons and neutrons dissolve. The quarks and gluons inside them form a hot, dense soup that physicists call a quark-gluon plasma, a state of matter that existed in the first microseconds after the Big Bang. That soup lasts for an almost unmeasurably short time, before expanding, cooling, and reforming into standard particles that fly outward into the detector. The entire process, from cold vacuum to 10 trillion degree plasma to particle spray, happens in a space smaller than an atomic nucleus and a time shorter than any clock can measure. And then the detectors record what came out. Every particle in that spray carries information: its direction, its energy, its charge. The pattern of how particles emerged from a single collision tells physicists what happened at the moment of contact. Buried in those patterns are the rare decay events that carry hints of hidden physics. But the scale of what the detectors are dealing with is hard to picture. And one way to make it concrete is to think about the energy in a single collision. There is a moment inside the collider that happens 40 million times per second and is over before the fastest thing in the universe could travel the width of a human hair. Two proton beams, each traveling in opposite directions around the 16.5-mile ring, meet at one of 4 crossing points. The protons are focused down to a beam width thinner than a human hair. Inside each beam, billions of protons are packed together, but they're still so small relative to each other that most pass through without hitting anything. Out of billions of near misses, a fraction of a percent actually collide. When a collision happens, the two protons don't bounce off each other like billiard balls. At these energies, they tear each other apart. The quarks and gluons inside each proton interact directly, releasing the energy of the collision in a spray of new particles. This is the moment the temperature reaches nearly 10 trillion degrees, and it happens in a space so small that comparing it to an atom is like comparing an atom to a football field. The energy released in a single proton collision is equivalent to the kinetic energy of a flying mosquito. That sounds small. A mosquito. But a mosquito's kinetic energy, distributed across the mass of a single proton, represents an energy density that existed in the universe only in the first microseconds after the Big Bang. Compressing a mosquito's flight energy into a subatomic space recreates the most extreme conditions the universe has ever experienced since its first instant. This is not an analogy. This is the actual physics. At that temperature and energy density, the quarks and gluons that were locked inside the two protons are no longer confined. They join a brief, expanding plasma of free quarks and gluons. The quark-gluon plasma, a state of matter that predates every proton and neutron in the universe. The plasma lasts for about 10 yoctoseconds, which is 10 to the power of negative 23 seconds, shorter than any other timescale in experimental physics. Then it cools, and as it cools, quarks recombine into new particles. Some of those particles are familiar: pions, kaons, protons, neutrons. Some are heavier and more exotic, living for only a tiny fraction of a second before decaying into lighter particles. And some are the ultra-rare events the experiments are hunting for, the specific decay patterns that might carry signals of physics beyond the standard model. The detector has to capture all of this within billionths of a second of the collision happening. Every layer of the detector serves a purpose in this capture. The innermost tracking layers record the precise paths of charged particles emerging from the collision vertex. The calorimeter layers measure how much energy each particle deposits. The outer muon detectors capture the particles that travel farthest before interacting with any material. Assembling all these signals back into a picture of what happened at the collision point is an act of reverse engineering the physics of the Big Bang, one collision at a time, 40 million times per second. The data from all those collisions, stacked, filtered, analyzed, and compared to standard model predictions, is what produces the hints currently making physicists nervous. And the sheer volume of that data is a challenge unlike anything in the history of computing. The collider does not just break physics records, it breaks data records too. Every year, the experiments at the facility generate over 90 petabytes of data. To put that in terms that connect to something real, a single petabyte is roughly equivalent to 10 billion photographs on a smartphone. 90 petabytes is 900 billion photographs. Stacked as printed photos, that pile would reach from Earth to the Moon and back several times over. And this is the data that survives the filter. The raw output, before any selection, would be orders of magnitude larger. The filtering system, called the trigger, is a real-time decision engine running at the speed of the physics itself. At the moment a collision happens, the trigger has roughly 1 microsecond to assess the initial detector signals, decide whether the event is interesting enough to save, and either record it or discard it permanently. Most events get discarded. The machine is designed to do this because saving everything would require a data pipeline too large to exist with current technology. The trigger is programmed to look for signatures that match theoretically important events, a specific pattern of particle tracks, an unusual energy distribution, a missing momentum signature that might indicate a particle escaped without interacting. Rare kaon decay patterns are on the trigger list. This creates a philosophical tension that physicists openly discuss. If something genuinely new shows up in the data but doesn't match any pattern the trigger was programmed to look for, the event gets deleted before anyone ever sees it. The trigger is designed based on current theories. It is, at some level, looking for what physicists already expect to find. With variations, something completely outside the theoretical framework might be systematically discarded by a filter that doesn't know to look for it. Researchers are aware of this problem and work to build as broad a trigger strategy as possible. But the fundamental constraint remains: you can't save everything. The 90 petabytes that do get saved flow into a computing grid spanning dozens of universities and research centers across the world. The facility operates one of the largest distributed computing networks ever built. Data from the collision hall in Switzerland arrives at computing centers in the United States, the United Kingdom, France, Germany, and elsewhere within seconds. Physicists at institutions worldwide analyze pieces of the dataset simultaneously. This distributed system allows the data volume to be processed, but it also introduces coordination challenges. Keeping analysis consistent across dozens of sites requires constant cross-checks. Systematic errors in one computing center's analysis need to be identified and corrected before they contaminate the global result. After all this filtering, transmission, storage, and analysis, the final output for a year of running might be a handful of numbers: branching ratios, cross-sections, angular distributions, small tables of measurements with error bars attached. Those numbers are compared to the standard model's predictions, and right now, some of those numbers don't match. The deviations aren't large enough yet to declare a discovery, but they're consistent enough, and they're pointing in a direction that, if confirmed, would require adding something fundamental to humanity's understanding of the universe. What that something is, nobody is sure, but one possibility being studied is so extreme that some physicists hesitate to say it in public. The possibility that the ground floor of reality itself is unstable. The universe feels stable. Stars burn for billions of years. Atoms hold together across geological timescales. The laws of physics appear consistent, whether you measure them here on Earth or observe them in light arriving from galaxies 12 billion light-years away. Everything around you suggests a cosmos built on a solid foundation, but there is a calculation physicists keep running based on the confirmed mass of the Higgs boson and the measured mass of the top quark that produces a result that is deeply uncomfortable to sit with. The calculation is about the energy state of the vacuum of space itself. In quantum physics, the vacuum is not empty. It is a seething field of energy, with particles constantly blinking in and out of existence, and fields permeating all of space. Every field has an energy state, and the lowest possible energy state a field can occupy is called its true vacuum. A field not sitting at its true vacuum is sitting at a higher energy, called a false vacuum. The field appears stable, can stay that way for an enormous length of time, but is always technically at risk of tunneling down to a lower energy state through a quantum process. Run the numbers using the Higgs boson's confirmed mass of about 125 giga-electron-volts, combined with the best current measurements of the top quark's mass, and the equations land in a zone physicists call metastable. The Higgs field may be sitting in a false vacuum, not at the absolute lowest energy it could occupy, sitting on a shelf above the true bottom, held in place by the shape of the energy landscape, but with a small non-zero probability of quantum tunneling downward. Think of a ball resting in a shallow bowl carved partway up a hill. It's stable in that bowl. It can sit there for billions of years. But the bowl has a wall, and if the ball crosses the wall, it rolls down to the actual valley floor below. The ball doesn't need to be pushed over the wall. In quantum mechanics, it can tunnel through. The universe may be that ball. Physicists are quick to stress several things. First, the timescale for any such tunneling event, if the metastable interpretation is correct, is likely to be vastly longer than the current age of the universe, potentially trillions upon trillions of years. Second, the calculation depends sensitively on the exact masses of the Higgs boson and the top quark, both of which have error bars that currently straddle the boundary between stability and metastability. Improve the measurements, and the answer might shift. The universe might turn out to be fully stable, but it might not, and the unsettling part is not the timescale, it is the mechanism. If a quantum tunneling event did occur, it would happen without any warning. There would be no signal, no observable precursor. A bubble of true vacuum would nucleate at a point in space and expand outward at the speed of light. The bubble wall would carry with it a region where the laws of physics are fundamentally different, where the strengths of forces, the masses of particles, and the rules governing chemistry and biology are all different from everything inside. Everything the bubble wall touched would be converted instantly. You would not see it coming. Light from the approaching wall couldn't outrun the wall. Physicists studying this possibility are not panicking, but they are measuring the Higgs mass and the top quark mass with increasing precision, because right now, the fate of the universe, according to the equations, depends on exactly where those numbers land, and the machine doing the measuring is about to get a significant upgrade. Picture the most dramatic explosion you can imagine. A nuclear weapon, a volcano, a gamma ray burst from a dying star millions of light years away. Every one of those events, as violent as they are, leaves the underlying laws of physics completely intact. Matter gets rearranged, energy gets released, but the rules governing atoms, the speed of light, the strength of gravity, remain unchanged throughout. A vacuum collapse would be different in kind, not just in scale. If the Higgs field tunneled from its current metastable state down to the true vacuum, the physics inside the expanding bubble would be governed by a completely different set of constants. The masses of particles would change. The strength of the electromagnetic force would shift. The balance between forces that allows atoms to form, that allows stars to burn, that allows chemistry to produce molecules, would all be different from anything in the universe we inhabit. Matter, as it currently exists, would cease to be viable. The bubble would expand outward from its origin point at the speed of light. This speed is important. It means the bubble can never be observed before it arrives. If the tunneling event happened in a galaxy 1 million light-years away right now, the bubble front would reach Earth in 1 million years, traveling at light speed, invisible in front of it. You can't see something moving toward you at the speed that carries all information. The transition, when it arrived, would be instantaneous from any observer's perspective. One moment, standard physics. The next, a universe with different rules. Physicists sometimes describe this as the ultimate cosmic reset. The bubble doesn't destroy the universe in the way a bomb destroys a building. It converts it, replaces the current physical laws with a different set, building an entirely different kind of universe behind it, one that operates by entirely foreign rules and almost certainly can't support anything resembling the structures that exist in ours. Now, before this image takes hold too firmly, several important things are worth placing alongside it. The scenario assumes the universe is genuinely in a metastable state, and that remains an open question. Current measurements of the Higgs mass sit close to the boundary between stable and metastable. Refining those measurements is an active priority at the facility. If the true mass turns out to be slightly higher than current central estimates, the stability calculation could shift to a fully stable result. There is also the question of whether the collider itself could trigger such an event. This has been studied carefully. The answer, based on the physics, is clearly no. The energy densities at the collider, while extreme by any human standard, are dwarfed by the energies of cosmic ray collisions that bombard Earth and every other object in the universe continuously. If collider-scale energies could trigger a vacuum collapse, cosmic rays would have triggered one long ago. The universe's age is evidence that the events happening at the facility are well within the safe zone. The measurement program continues. Higgs mass, top quark mass, precision decay experiments. Each measurement tightens the constraints on the stability calculation, but the outcome isn't confirmed yet. And the thing that determines the outcome most precisely is a number that was already found, a number with mass. And learning exactly how precise that number needs to be is the next frontier. One number, one measurement, the fate of the universe's stability sitting on its decimal places. When physicists confirmed the Higgs boson in 2012, the immediate celebration was about completing the Standard Model's roster of particles. The Higgs was the last predicted piece. Finding it felt like closing a chapter. What the physics community didn't emphasize loudly in the public celebration was what the specific mass implied: 125 giga-electron volts. That number placed the Higgs boson right at the edge of a stability cliff. Here's the picture. Imagine a stability chart where the horizontal axis is the Higgs boson mass and the vertical axis is the top quark mass. The chart has three regions: a fully stable zone, a fully unstable zone, and a metastable zone in between. Fully stable means the Higgs field sits in an absolute energy minimum and stays there forever. Fully unstable means the field would have already collapsed long ago. The universe wouldn't exist if it were there. Metastable means the field is in a local minimum that looks stable but isn't the deepest possible state. It can last an enormously long time, but given infinite time, or given a sufficiently energetic quantum fluctuation, it collapses. The measured values of the Higgs boson mass and the top quark mass currently place our universe in the metastable region, close to the boundary with fully stable, but inside the metastable zone according to the best current measurements. The closeness to the boundary is actually interesting to physicists for a different reason. Sitting near the edge of stability could itself be a clue. Some physicists think this near criticality is connected to deeper physics at very high energies. The suggestion is that additional interactions, perhaps the kind occurring in the Zeptuniverse, stabilize the Higgs field in a precise way that happens to land the mass very close to the edge of stability. If that's right, the metastability is a feature, not a danger signal, a sign that something deeper is at work. Improving the Higgs mass measurement is therefore valuable in two ways. It either shifts the stability calculation toward the safe zone, reducing the theoretical concern, or it confirms the metastable picture more precisely, giving physicists stronger constraints on what kind of new physics would be needed to stabilize it. The high luminosity upgrade of the collider will produce millions of Higgs bosons where the current machine produces thousands. That flood of new data allows the mass to be pinned down to a precision that isn't currently achievable. Small refinements in the mass measurement could move the universe's position on the stability chart in ways that change the theoretical picture significantly. 1 decimal place on a particle's mass, measured 100 meters underground, potentially revealing whether the ground floor of physics is solid or hollow. The precision required for that measurement demands far more collisions than the current machine can produce, which is why, starting in 2026, the collider is going quiet. In 2026, they switch it off. The proton beams stop. The cryogenic cooling systems are partially warmed. Thousands of engineers and technicians descend into the 16.5-mile tunnel, carrying equipment, tools, and years' worth of maintenance plans. The world's most powerful particle accelerator enters its longest planned shutdown since the beginning of operations. Long Shutdown 3 is not a pause. It is a transformation. The goal is to prepare the facility for its most ambitious upgrade yet. Every component that limits the number of collisions the machine can produce needs to be either replaced or modified. Magnets near the 4 collision points will be swapped out for a new generation of superconducting magnets, built with technology that didn't exist when the original machine was commissioned. These new magnets are stronger. Stronger magnets focus the proton beams more tightly. A tighter beam means more protons pass through the same microscopic collision zone per second, which means more collisions. The inner detectors at the largest experiments are also being rebuilt. The innermost tracking layers take enormous punishment from the intense radiation produced by millions of collisions per second. After years of running, radiation damage degrades their precision. The upgrade replaces them with new silicon tracking detectors capable of operating at the higher collision rates the upgraded machine will produce. New electronics throughout both large detectors will also be installed. The trigger systems that decide in microseconds which events to save need to be upgraded to handle a data rate 10 times higher than what the current systems process. This requires custom-designed chips capable of faster processing, running algorithms more sophisticated than anything deployed in the existing detectors. The shutdown is scheduled to last until approximately 2029. 3 years of construction inside a tunnel that requires specialized training just to enter. Teams from dozens of countries coordinate through a project management structure designed to keep thousands of parallel tasks moving without collision. During this period, no new physics data comes from the main experiments. The scientific community shifts its focus toward analyzing the enormous data sets already collected and publishing results from years of previous runs. Papers continue to emerge. Anomalies get studied with more sophisticated analysis tools. The kaon decay results and the hints in the B meson sector get scrutinized by theorists, building models of what might explain them. The physics community uses the shutdown productively, but there is a quiet urgency underneath the activity. because the shutdown is preparation for something that physicists believe could finally push the measurements past the threshold that current data can't cross. The upgraded machine will be capable of generating 10 times more collisions every second than the current version. 10 times more collisions means 10 times more rare events, 10 times more kaon decays, 10 times more Higgs bosons, 10 times more chances to catch the signal that the current dataset is only hinting at. If the deviations seen so far are real, the upgraded machine will confirm them with enough certainty to officially break the standard model. If they vanish with more data, it tells physicists something equally important. The anomalies were statistical noise, and the search needs to go somewhere else. Either outcome changes physics, but the outcome that physicists are most quietly hoping for, the one that would reshape everything, requires the upgraded machine to catch something no detector has ever caught before. Luminosity is the word physicists use for collision rate. A high luminosity machine is one that produces an enormous number of collisions per unit time, and the upgrade coming after Long Shutdown 3 will make the current collider look, by comparison, like a first draft. The High Luminosity Large Hadron Collider is scheduled to begin data collection around 2029. When it does, the collision rate will be 10 times higher than the original machine's design peak. Billions of collisions every second, sustained over years of running. The physics case for this increase is direct. Every rare process the facility studies improves in statistical precision as the number of observed events grows. A signal showing up at 2 standard deviations of significance in the current dataset, close to interesting but short of compelling, becomes 5 standard deviations in the upgraded data if the deviation is real. 5 standard deviations is the threshold particle physics uses for an official discovery claim. It means the probability of the result being a random fluctuation is less than 1 in 3 million. The kaon anomaly from the NA62 experiment, the B meson rate deviations, the Higgs mass measurements sitting near the stability boundary. Every one of these gets pushed across or firmly away from the discovery threshold once the upgraded machine runs at full luminosity for several years. But the upgrade isn't just about measuring known hints more precisely. It's about reaching into regions of physics currently invisible. The collider's detectors have a dark zone, regions of parameter space where the signals of new particles would be too rare or too subtle for the current machine to collect enough examples. The standard model extensions that theorists have built to explain dark matter, or the matter-antimatter imbalance, or the kaon anomalies, all predict additional particles and interactions. Many of those predictions place the new particles in mass ranges the current machine can produce but can't study with sufficient statistics. The high luminosity upgrade pushes those regions into full view. A particle that might appear once in every 10 billion collisions at the current machine becomes observable in a statistically meaningful sample after years of running at 10 times the collision rate. The magnets driving this upgrade are a significant engineering achievement on their own. The new focusing magnets near the collision points use a niobium tin alloy that can carry higher electrical currents than the niobium titanium magnets used in the original machine. Higher current means stronger magnetic field. Stronger field means tighter beam focus. Tighter focus means more protons overlapping in the same collision region per second. Niobium tin is harder to manufacture and more brittle than the original magnet material. Bending it into the precise coil shapes required for focusing magnets required new fabrication techniques developed specifically for this upgrade. Hundreds of these magnets have been built at facilities across the world and will be installed during the shutdown. When the machine restarts, the physics community will have access to a data stream that is categorically different from anything collected before. And several of the first targets on the physics list touch directly on the zones of the universe that the current experiments can barely see at the edge of their sensitivity. The dark sectors. There are parts of the universe the current detectors can feel but not see. Physicists call them dark sectors. The phrase covers a collection of theoretical ideas about physics that operates outside the known particles and forces of the standard model. but at energy scales the collider can actually reach. The term dark here doesn't necessarily mean darkness in the visual sense. It means hidden, decoupled, interacting with normal matter so weakly that the interaction barely registers. The search for dark sectors looks different from the search for the Higgs boson or a standard heavy particle. Those particles decay quickly into well-known final states that light up the detector in clear patterns. Dark sector particles, if they exist, might travel significant distances before decaying, or decay into combinations of particles that are harder to distinguish from background processes. They might produce displaced decay vertices, meaning the decay happens not at the collision point, but at a measurable distance away inside the detector. The facility has several specialized experiments designed for exactly this type of search. One of them, called FACER, sits in a narrow tunnel more than 1,500 feet away from the main collision point. The experiment is designed to catch particles so weakly interacting that they travel the entire length of the tunnel and only decay inside the small detector at the far end. Catching even a handful of these events would be evidence of physics operating in the dark sector. Another experiment, called the scattering and neutrino detector, looks for neutrinos produced in the collision zone that then interact in a dense tungsten block farther along. Neutrinos are the classic dark sector particle in the sense that they interact with normal matter so feebly that trillions of them pass through your entire body every second without touching a single atom. Measuring neutrinos produced directly at the collision point allows physicists to test whether the neutrino behavior matches expectations or shows signs of additional mixing with hypothetical heavier partners. These heavier neutrino partners, sometimes called sterile neutrinos, are one of the most promising candidates for both dark matter and for the extra charge parity violation needed to explain the matter-antimatter imbalance. If sterile neutrinos exist and mix with regular neutrinos in measurable ways, their influence would show up as subtle deviations in neutrino detection rates across different experiments. The current collider has placed limits on where these particles can be hiding. It has ruled out large regions of the parameter space, where theorists initially expected to find them, but it hasn't ruled out the full territory. The high luminosity upgrade extends the search into the regions current data can barely probe. Dark sectors represent the possibility that the universe has entire categories of particle and force that are real, physically present, influencing matter and gravity, but essentially transparent to everything we've built to detect them. The matter you're made of, the light that lets you see, the forces that hold atoms together, might all exist in a small, bright corner of a much larger physics. And the edge of that larger physics might be visible, just barely, to an experiment running right now on the collider floor. Every second, approximately 100 trillion neutrinos from the sun pass through your body. 100 trillion. Every single second. They enter from above, pass through your skin, your organs, your bones, and exit through the ground below you. Your body is essentially transparent to them. So is the Earth. A neutrino traveling at nearly the speed of light can pass through a block of lead 1 light-year thick and have roughly even odds of interacting with a single atom. This near-complete invisibility makes neutrinos one of the most maddening particles in physics. They were theorized in 1930 by physicist Wolfgang Pauli, who proposed their existence to explain why energy seemed to go missing in certain radioactive decays. He predicted a particle so undetectable he initially believed it could never be confirmed experimentally. He almost apologized for proposing it. Neutrinos were experimentally confirmed 26 years later, using a detector placed near a nuclear reactor, where the flux of neutrinos was high enough that occasional interactions became measurable. Since then, physicists have learned a great deal about neutrinos. They come in 3 varieties, called flavors: electron neutrinos, muon neutrinos, and tau neutrinos. And as neutrinos travel, they oscillate between these flavors. An electron neutrino produced at the sun's core might arrive at Earth partly converted to a muon neutrino. This oscillation is confirmed and was awarded the Nobel Prize. The oscillation itself is remarkable because it proves something the Standard Model originally assumed to be false. Neutrinos have mass. The original version of the Standard Model assigned neutrinos zero mass. The observation of flavor oscillation requires mass, and so the Standard Model had to be extended. This extension is the source of deep theoretical discomfort. The mass of neutrinos, while confirmed to exist, is extraordinarily small, millions of times lighter than the electron, which is already the lightest known massive particle. No theoretical mechanism in the Standard Model naturally produces such a small mass without what physicists consider a severe fine-tuning problem. The leading explanation for why neutrino masses are so tiny is a mechanism called the seesaw mechanism. The idea is that the neutrinos we observe are light because they're partnered with an extremely heavy version, a sterile neutrino, and the two masses balance each other mathematically. The heavier the sterile neutrino, the lighter the observable one. If sterile neutrinos exist and are in the right mass range, the collider can search for them. They would be produced occasionally in high-energy collisions and would travel invisibly through the detector. But their existence would manifest as missing energy, and their eventual rare decays, if they happen inside the detector, would produce distinctive signatures. Finding sterile neutrinos would simultaneously explain the lightness of observable neutrinos and potentially provide the additional charge parity violation needed to explain why matter survived the Big Bang. Two of the biggest mysteries in physics. One proposed particle that might connect them both. The search continues, and the stakes underneath it are higher than almost anything else the facility is chasing. Running the most complex machine ever built costs roughly the same as powering a small city for an entire year. The facility uses approximately 1.3 terawatt-hours of electricity annually. That number sits alongside cities of around 300,000 people. During peak physics runs, the power demand spikes higher, and the facility works with regional energy providers to manage the draw against the grid. This consumption isn't waste. Almost every component of the machine either requires enormous power to operate or requires enormous power to keep cool. The superconducting magnets need continuous refrigeration to stay at -456 degrees Fahrenheit. The cryogenic systems running that refrigeration are themselves massive engineering structures. The radio frequency cavities that accelerate the proton beams use high-power radio waves to push the protons forward on every loop around the ring. The computing grid processing 90 petabytes of data annually runs continuously across dozens of sites worldwide. The facility is aware of its energy footprint. Engineers have pursued efficiency improvements in the cryogenic systems, the computing infrastructure, and the accelerator systems over successive operational years. The high luminosity upgrade includes provisions for more energy-efficient magnet cooling designs. But the fundamental physics of what the machine does, generating the highest energy particle collisions ever achieved by human technology, requires energy. There is no low-power shortcut to the Zeptuniverse. The antimatter produced at the facility illustrates the energy cost of this physics in a different way. The facility produces small quantities of antihydrogen and other antimatter particles as byproducts of certain experiments. If you collected every single antiparticle ever created at the facility across its entire operational history, every antiproton, every positron, every antihydrogen atom, and annihilated them all simultaneously with matter, the total energy released would be insufficient to power a single light bulb for even a short time. This is the scale at which physics operates when it's probing the fundamental structure of matter. The experiments are extraordinarily sensitive. The signals being hunted are microscopic, but the machine required to reach those signals is enormous, expensive, and power-hungry, and the components that make the measurements themselves are physically remarkable. Inside the detectors sit materials that seem to violate common intuition just by existing. The lead tungstate crystals at the heart of the electromagnetic calorimeter inside the CMS detector are completely transparent to visible light. You could hold one up and look through it like glass. But the same crystal is roughly 8.5 times denser than water and significantly heavier than solid iron. Thousands of these crystals, each about the size and shape of a thick marker, pack into the calorimeter structure and flash with tiny bursts of blue and ultraviolet light whenever a particle deposits energy inside them. Every flash is digitized, every pattern of flashes reconstructed into a particle track, every track folded into the statistical analysis, hunting for deviations from the standard model. And those deviations, when they show up, arrive in the form of numbers that the physics community then debates fiercely, because the difference between a real signal and a statistical fluctuation can be a matter of a fraction of a percentage point. That debate is one of the most productive and contentious conversations in modern science. Particle physics has a word for getting it wrong in a visible way. It's called a 3 sigma result. In statistics, sigma measures how far a result sits from the expected baseline in units of standard deviation. A 1 sigma deviation happens about 30% of the time by pure chance, even with no real signal present. A 2 sigma result is a bit unusual. A 3 sigma result, meaning the measurement sits 3 standard deviations away from the prediction, happens roughly once in every 300 measurements by chance. 3 sigma results have a history in particle physics of generating excitement and then disappearing. In the early 2000s, several experiments reported 3 sigma hints of new particles that vanished when more data arrived. In 2015, an excess appeared in the Large Hadron Collider data, suggesting a possible new particle at a specific mass. Papers flooded the physics community, exploring theoretical explanations. Several hundred papers were written in the months following the result. The excess disappeared entirely in the next dataset. The particle didn't exist. This history makes physicists extremely cautious about any result below 5 sigma, 5 standard deviations of significance. The probability of a 5 sigma result occurring by random fluctuation is less than 1 in 3 million. The threshold is deliberately high because the cost of a false discovery, years of theoretical work chasing something that doesn't exist, is enormous. The current anomalies in kaon decays and B meson rates sit in a range that particle physicists treat seriously but not yet as confirmed. The Na62 kaon result and several B meson measurements from a dedicated flavor physics experiment are showing consistent deviations in the same direction across multiple channels. This consistency across independent measurements is the most persuasive feature of the current situation. A random fluctuation in one experiment is unsurprising. The same fluctuation appearing in the same direction in 5 different measurements of different particles, run by different teams using different methods, is substantially harder to dismiss. Theorists are divided. Some argue the pattern is compelling enough to take seriously as a signal of new physics, and have built detailed models of what particles or forces could explain the combined picture. Others argue that the individual measurements, while each interesting, don't yet individually clear the bar required for confidence, and that the apparent pattern could still dissolve with more data. Both camps agree on what resolves the question: more statistics. The high luminosity upgrade provides exactly that. If the combined significance of the B meson and kaon anomalies passes 5 sigma after several years of running at 10 times the current collision rate, the standard model is officially broken. New physics is confirmed. The field restructures around the discovery. If the anomalies fade toward the prediction as statistics improve, the current hints were noise, and the search continues in a different direction. Either result is scientifically valuable. The worst outcome in physics is ambiguity, and the upgrade eliminates ambiguity by sheer statistical force. But physicists are already thinking past the question of whether the standard model breaks. They're thinking about what happens after it does. The standard model has been stressed before. In the 1970s, the electroweak theory that unified electromagnetism and the weak nuclear force was confirmed. It required extending the existing framework. In the 1980s, evidence for 3 generations of quarks forced the model to accommodate more structure than originally expected. Each time new data demanded something new, physicists absorbed it by adding to the framework. The anomalies building now feel different to many researchers. The combination of unexplained dark matter, the matter-antimatter imbalance, the neutrino mass problem, the Higgs stability question, and the rare decay deviations all pointing in the same direction suggests the current framework is missing something structural. The pattern of problems looks less like a gap to fill and more like a sign that the entire organizing principle needs revision. What would that revision look like? Several serious theoretical frameworks exist. Supersymmetry proposes that every known particle has a heavier partner particle related by a symmetry between matter and force. These partners would solve the Higgs stability problem, provide dark matter candidates, and generate additional charge parity violation. The Large Hadron Collider has searched for supersymmetric particles across a wide mass range and found nothing yet. The absence has killed the simplest versions of the theory, but left more complex versions alive. Composite Higgs models propose that the Higgs boson is not a fundamental particle, but is itself built from smaller constituents, bound together by a new, undiscovered force. This structure naturally explains why the Higgs mass sits where it does, and predicts new resonances at energies the high luminosity machine can probe. Extra dimensions of space, proposed in several theoretical frameworks, would change how gravity and other forces behave at short distances and could explain why gravity is so much weaker than the other forces. Some extra dimension models predict the appearance of towers of heavier partner particles for known particles, called Kaluza-Klein modes, at mass scales potentially accessible to the upgraded machine. None of these frameworks has been confirmed. Each makes specific predictions that the upgraded machine will test with unprecedented precision. The experience of the last 15 years of collider data has taught physicists humility. Many theorists expected the original collider to find supersymmetric particles almost immediately. The absence forced a significant recalibration of theoretical expectations. The new models coming from this period tend to be more careful, more flexible, more focused on observable consequences rather than elegant theoretical aesthetics. Whatever the correct theory beyond the standard model turns out to be, it has to explain why the standard model works so well at currently tested scales while failing at the deepest scales. That's an extremely tight constraint. Most theories that technically extend the standard model fail this constraint by predicting effects that should have already shown up in existing data. The theory that passes this constraint, if it exists, will be one of the great intellectual achievements in the history of science. And the machine currently being prepared for its biggest upgrade yet is the instrument most likely to find the first solid sign of what that theory needs to contain. The universe has 4 known forces. Gravity holds planets in orbit and pulls you to the ground. Electromagnetism carries light, drives chemistry, and makes every electrical device work. The strong nuclear force locks quarks together inside protons and neutrons with an intensity that makes it the most powerful force in the known universe at short range. The weak nuclear force drives certain types of radioactive decay and played a central role in the nuclear reactions of the early universe. 4 forces, described by the standard model, plus general relativity for gravity. That framework accounts for every physical phenomenon ever directly observed by human instruments. Physicists have strong reasons to think there are more. The theoretical problem with just 4 forces is that gravity is wildly weaker than the others. Hold a paperclip. A refrigerator magnet can lift it off the table, overcoming the gravitational pull of the entire Earth on a tiny piece of metal. Gravity operates across cosmic distances and organizes galaxies, but at the particle scale, it is negligibly faint compared to electromagnetism or the nuclear forces. This enormous gap between gravity's strength and the others is called the hierarchy problem. The hierarchy problem suggests either that something is fine-tuned to an absurd degree in the fundamental equations, or that additional physics exists, which connects the different scales and explains why gravity appears so weak. Many of the theoretical extensions of the Standard Model were built specifically to address this problem. Supersymmetry does it one way, extra dimensions do it another. Composite Higgs models take a different approach. Each proposed solution predicts specific observable consequences: new particles at specific mass ranges, new interactions between known particles, modified rates for specific processes. The collider tests these predictions directly, but some researchers are now exploring possibilities that go beyond adding particles to the existing framework. They're asking whether the forces themselves might be different from what we think at the very smallest scales. Whether the way the four forces unify or fail to unify might reveal a deeper structure. Grand unified theories attempt to show that the strong force, the weak force, and electromagnetism are all expressions of a single underlying force that operated as one in the very early universe and split apart as the universe cooled. These theories predict that protons, which the Standard Model considers perfectly stable, should actually decay, but with an extraordinarily long half-life. Experiments searching for proton decay have run for decades without finding it. This places tight limits on many grand unified theories. A theory that successfully unifies all four forces, including gravity, into a single framework is sometimes called a theory of everything. No such theory exists in confirmed form. String theory is the most developed attempt, but it currently makes predictions at energy scales far beyond any conceivable collider. The high luminosity era won't reach a theory of everything, but it will push into energy and precision ranges where the first signs of unification or new forces might appear. A single confirmed anomaly, passing the 5 sigma threshold, would give theorists a real target to aim for instead of a vast open landscape. And one of the specific targets, sitting at the intersection of almost every open question in physics, is the particle that most physicists believe must exist, but that no experiment has ever captured. Dark matter has to be something. Physicists sometimes say this with a tone of exasperation, because the evidence for dark matter's existence is overwhelming, yet every direct detection attempt has come back empty. The particle, if it is a particle, is there. The gravitational evidence is unambiguous, but it refuses to appear in any detector. The leading candidate for decades was a class of particles called weakly interacting massive particles. The theoretical appeal of these particles was strong. If you extended the Standard Model in certain natural ways, particularly through supersymmetry, you automatically got a new heavy particle that interacted only through the weak force and gravity. This particle would be stable, invisible to light, produced in the right quantities in the early universe, and present in the right amounts to explain the dark matter observations. The pieces fit almost too cleanly. Experiments went looking. Underground detectors filled with liquid xenon, designed to catch the rare occasion when a dark matter particle bounced off an atomic nucleus, ran for years. Nothing. Larger detectors ran for longer. Still nothing. The collider searched for missing energy signatures that would indicate dark matter particles created in collisions, and then escaping the detector invisibly. Nothing. The absence of weakly interacting massive particles in detector after detector, including the Large Hadron Collider across 2 full-run periods, has pushed physicists to take seriously the alternatives they previously treated as less elegant. Axions are one alternative, originally proposed to solve a different problem in quantum chromodynamics, the theory of the strong force. Axions are extremely light particles that would interact with photons in the presence of a strong magnetic field, converting briefly into detectable light. Several experiments worldwide are hunting for this conversion. Some have recently placed the tightest constraints yet on where axion dark matter could be hiding. The search continues. Primordial black holes are another alternative. If conditions in the very early universe produced a large population of tiny black holes before any stars formed, Those black holes could provide the missing mass without being particles at all. Observations of gravitational microlensing events and gravitational wave detections are being used to constrain how much of the dark matter could be in this form. None of these candidates is confirmed. Each has theoretical appeal and experimental programs pursuing it. The High Luminosity Collider will probe weakly interacting massive particle parameter space more deeply than ever before. If the particle exists in the mass ranges still allowed by current limits, a decade of running at 10 times the current collision rate should either find it or push it into regions so exotic that most theoretical motivations for the particle would disappear. That outcome, a definitive non-detection across the entire theoretically motivated mass range, would be one of the most important negative results in physics history. It would kill the most popular explanation for dark matter and force the community to fundamentally reconsider what the invisible majority of the universe is made of. Whatever dark matter is, it's out there, surrounding every galaxy, passing through the Earth continuously, and the answer to what it actually is will reshape physics completely. The only thing standing between us and that answer is precision and time. There is a number that appears in the Standard Model and has no explanation. Physicists call it the cosmological constant. Einstein introduced it first as a term in his equations for general relativity to keep the universe from collapsing under its own gravity. He later called it his greatest blunder when observations revealed the universe was actually expanding. But then, in 1998, two independent teams measuring the distance and speed of distant supernovae discovered something that changed everything. The universe is expanding, and the expansion is accelerating. Something is pushing space apart with increasing force. The cosmological constant came back, not as Einstein's blunder, but as the mathematical description of something physically real. Physicists now call this accelerating expansion dark energy, and the cosmological constant is their best mathematical handle on it. The problem is the number. Quantum field theory, the framework underlying the Standard Model, predicts a value for the energy density of empty space based on the quantum fluctuations of all the fields that fill it. When physicists calculate this predicted value and compare it to the observed cosmological constant, the two numbers disagree by a factor of 10 to the power of 120. That is not a typo. 1 followed by 120 zeros. The worst prediction in the history of physics, by an almost inconceivable margin. Something is cancelling the enormous predicted vacuum energy down to the tiny observed value with extraordinary precision. A cancellation of 120 orders of magnitude requires a mechanism. The Standard Model provides no mechanism. This failure has been known for decades. Physicists call it the cosmological constant problem, and it remains completely unsolved. Some researchers believe the solution involves a symmetry that sets the vacuum energy to exactly zero, with a small additional contribution from something else providing the observed dark energy. Others invoke the anthropic principle, arguing that we observe the value we observe because only universes with small cosmological constants can form galaxies and stars and observers. Neither answer is satisfying to most physicists. The first requires discovering a symmetry that no current theory contains. The second is philosophically uncomfortable and resists experimental testing. The collider cannot directly measure the cosmological constant, but the new physics it's hunting for, whatever explains the kaon, anomalies, or dark matter, or the Higgs stability, might connect to the mechanism that controls the vacuum energy. Theories that address the Higgs hierarchy problem often have implications for the cosmological constant problem as well. The two problems may not be separate. They may be two symptoms of the same missing piece, and the physicist community's growing willingness to discuss both together reflects a broader shift. The sense that the collection of open questions has grown large enough that a single, deeper explanation connecting all of them is more likely than a series of independent patches. That deeper explanation, if it exists, is waiting just beyond the current reach of every instrument ever built. Physics discoveries don't arrive with explosions. The Higgs boson discovery in 2012 was announced in a crowded auditorium with a slideshow. The result was a set of data points on a graph, a bump in a plot of particle collision rates at a specific energy, rising above the expected background with enough statistical significance to cross the 5 sigma threshold. The bump was the particle. The celebration was enormous. The graph itself looked unremarkable to anyone who wasn't a physicist. A future discovery of new physics beyond the standard model will look similar. A deviation in a measurement of kaon decay rates crossing from 2 sigma to 3 sigma to 4 sigma to 5 sigma as data accumulates over years. Or a new resonance appearing in the collision products at a mass no known particle occupies. Or a systematic missing energy signal that grows more significant with every additional run period. The process is slow, deliberate, layered with cross-checks. When a potential signal appears, the team that found it doesn't immediately go public. Internal reviews begin. Independent subteams within the same experiment reanalyze the data using different methods. Systematic uncertainties are stress-tested. Every known source of background is re-examined to make sure the signal isn't an artifact of how the data was processed. If the signal survives internal review, a paper is prepared and submitted to a journal. Other experiments, running similar analyses, are asked to check their data for the same signal. The peer review process begins. Outside, theorists start building models to explain the signal if it's real. The wider physics community discusses the result in conference talks and workshop papers. Only after independent confirmation from a second experiment, or after the same experiment accumulates enough data to push the significance past 5 sigma beyond any reasonable doubt, does the result cross the threshold into accepted discovery. This process protects physics from false discoveries. It's slow and sometimes frustrating, but it's also why the discoveries that do clear the bar are extraordinarily reliable. A confirmed discovery of new physics at the collider would cascade through the entire scientific world. Every theorist who has built a model predicting something in that region would immediately check whether their model fits the new data. Those whose models fit survive. Those whose models don't are revised or abandoned. The winning model, or family of models, becomes the new target for experimental tests. Experiments at other facilities worldwide would be redesigned to probe the implications of the discovery. Funding for new instruments would accelerate. The question physics has been building toward for decades, what lies beyond the standard model, would finally have an empirical foothold, and the answer to that question opens a set of further questions that physicists are already writing down, waiting for the day they have a discovery to anchor them to reality. There is a question that sits quietly at the edge of every major unsolved problem in physics. Is the standard model the kind of theory that can be fixed by adding pieces? Or is it the kind of theory that is fundamentally the wrong kind of story about reality? The history of science has examples of both. Sometimes a theory is mostly right and just needs extension. Newton's gravity was mostly right. Einstein's general relativity extended it to cover cases Newton didn't handle: high speeds, strong gravitational fields, the large-scale structure of the universe. But Newton's equations didn't disappear. They remain accurate and useful within their domain. General relativity contains Newton's gravity as a special case at low energies. Other times, a theory is wrong at a deeper level. The idea that Earth sat at the center of the solar system wasn't fixed by adding epicycles to the planetary orbits. Even though adding epicycles improved the predictions temporarily, the organizing principle was wrong. Replacing it with a sun-centered solar system wasn't an extension, it was a replacement. Some physicists worry that the standard model is the epicycle situation, that the framework of point particles, quantum fields, and the current conception of space and time is the wrong language for describing nature at the deepest level. That the new physics waiting beyond the current detection limit won't fit neatly onto the current framework, but will require a completely different mathematical starting point. String theory was once hoped to provide that starting point. It replaces point particles with one-dimensional strings vibrating at different frequencies, naturally incorporating gravity alongside quantum mechanics. It predicts the existence of extraspatial dimensions and a vast landscape of possible universes with different physical laws. But it makes predictions at energy scales many orders of magnitude beyond any foreseeable experiment, making it currently untestable. The physics community is genuinely divided about whether string theory is the future of fundamental physics or an elegant mathematical dead end. The honest answer to the question of whether the standard model is fixable or replaceable is that nobody knows. The answer depends on what the anomalies currently showing up in the data turn out to be. If the new physics discovered by the high luminosity upgrade is a new particle or force that fits naturally into an extended quantum field theory, the standard model gets extended. If the new physics is stranger, if it points towards structures that resist incorporation into the current framework, the replacement scenario becomes more compelling. Physicists are genuinely afraid of the replacement scenario, not because they don't want to discover new physics, but because a replacement would mean decades of theoretical work built on the current framework needs to be revisited. Careers spent developing particular mathematical tools might turn out to be irrelevant to the actual structure of the universe. The intellectual cost of a paradigm replacement is enormous. And yet, every major revolution in physics required exactly that cost, and every revolution produced a deeper, more powerful understanding of reality than what it replaced. The collider is, at this moment, generating the data that will eventually answer the question. The high luminosity era will run through the late 2030s and into the 2040s. During that time, physicists will collect more collision data than in all previous decades of accelerator physics combined. Every open question currently sitting at the edge of the standard model will be pushed to its limit. Dark matter searches will either find something or rule out the most plausible candidates completely. The Kaon and B meson anomalies will either become confirmed discoveries or fade into the background. The Higgs boson's mass will be pinned to a precision that settles the stability question. The dark sectors will either reveal new structures or demonstrate their absence up to the machine's maximum reach. At the end of that program, physicists will know far more than they do today. But they already know that whatever they find, it won't be the final answer. Every discovery in physics history has opened more questions than it closed. The discovery of the electron revealed the atom's structure, but prompted 50 years of work to understand quantum mechanics. The discovery of quarks solved the mystery of why there were so many different hadrons, but launched decades of work on the strong force. The Higgs boson confirmed the mechanism of mass generation, but raised the stability question and left dark matter completely unexplained. The physics community is already in early discussions about what comes after the high luminosity era. A next generation of colliders is being proposed at several scales. One concept, being developed through an international collaboration, would be a circular machine with a circumference of nearly 60 miles, more than 3 times longer than the current tunnel, capable of reaching collision energies many times higher than anything achievable today. This machine would take decades to build and cost more than any physics instrument ever constructed. Another concept proposes using laser-driven plasma waves to accelerate particles, potentially achieving the same collision energies in a machine physically small enough to fit inside existing buildings. This technology exists in prototype form, but requires decades of development before it could reach the energies needed for fundamental physics. A third approach focuses on colliding muons instead of protons. Muons are heavier cousins of electrons, and muon collisions produce cleaner signals than proton collisions because muons are point-like particles rather than composite ones made of quarks. A muon collider could reach very high effective energies in a compact ring. The technical challenges are extreme, since muons decay in microseconds, but the physics case is compelling. Each of these machines represents a choice about what questions to prioritize. The choice depends on what the high luminosity era finds. If specific new particles appear at accessible energies, the next machine gets designed to study them in detail. If the result is absence, the next machine needs to reach higher energies to push into unexplored territory. The decision about which machine to build will be made by the scientific community sometime in the 2030s, informed by data that doesn't fully exist yet. What physicists agree on is this: the questions now sitting unanswered are not technical details. They are questions about the fundamental nature of matter, energy, space, and time, about why the universe exists in the form it does, about whether the laws of physics are stable across the entire cosmos, or just stable in our corner of it. The machine buried under Europe is one step in a search that will outlast every person currently working on it. The universe has been hiding its deepest rules for 13.8 billion years. Physicists have been asking questions for a few centuries. The conversation is just beginning.